All right, welcome to our second webinar on the topic of water in mine operations and slope stability. Today we'll be talking about water in mining, water management strategies. We have a panel of hydrogeological experts in mining water management, and they are here today to answer questions and discuss topics on this topic that we are discussing today. And I will introduce them in just a moment. But first, this webinar is developed by the Geotechnical Center of Excellence here in Tucson, Arizona. We are an industry-funded and member-led interdisciplinary center, and we use a collaborative and practical approach to geotechnical research and education with the goal of bridging gaps between academia, industry, and fields of study. If you would like to know more about the GCE, you can send us an email here at gce@arizona.edu. And as I mentioned, we are member-led and member-supported, so I'd like to take a moment to acknowledge all of our member companies that support our research and our educational initiatives, such as the courses that we put on and webinars such as this. So thank you very much to our GCE membership group. We appreciate your support. And the topic of this course aligns with this webinar aligns with one of our professional development courses, which are available online. And this course is the Water and Mine Operations and Slope Stability course. Everything is online in a learning portal. We go over a comprehensive list, as you can see here, of different topics related to water in mine operations and slope stability. This course is currently open for registration, and you can either scan the QR code here or you can go to our website to see this course and many other courses that we offer, and that's mining.arizona.edu/GCE. So now I'll introduce our webinar team from the GCE. I am Jillian Noonan. I'll be your moderator today. I'm Senior R&D Engineer with the GCE. And today, also with me, I have Julia Potter, who is the Director of the GCE. Julia, thanks for joining today.
Thank you, Jill. Hello, everybody. Thanks for being here today.
And Cheryl Bukowski, who is our Professional Development Program Lead, helps to guide our course program. Cheryl, thanks for being here.
Thank you, Jill, and welcome everyone.
And we also have Alma Riesener, who is an undergraduate researcher with the GCE, and she helps with both research and also with our courses. Thanks, Alma, and our webinars. Thanks for being here today, Alma.
Hi, good morning, everyone.
And now it's my pleasure to introduce the panel that we have present that will be addressing your questions. Firstly, we have Jeff Beal. Jeff is the Global Technical Advisor with Pateau Associates and also one of the primary presenters in the course that I mentioned, Water in Mine Operations and Slope Stability. Jeff, always good to have you. Thanks for being here.
Thanks, Gillian, and welcome everybody. This hopefully will be a good session.
Definitely will. Jeremy Dowling. Jeremy is the Hydrogeology Advisor and President with Pateau Associates, and also one of the primary presenters in the Water and Mine Operations and Slope Stability course. Jeremy, great to have you here today. Thanks for joining the panel.
Yeah, hi everyone. Nice to be here.
Simon Scholl. Simon is Principal Hydrogeologist with Pateau Associates and also presents some nice modules in the course. Simon, glad to have you on our panel today.
Thanks, Jill. Hi, everybody. Looking forward to it.
Travis White. Travis is a principal hydrogeologist with Anglo American and also a presenter in the water course. Travis, good to have you here today.
Hi, and welcome, everyone. Always a pleasure to be here.
And we're also fortunate to have with us today Christian Sintelacy, who is principal hydrogeologist with Anglo American. Christian, thank you so much for being here.
Thanks, Jill. Hey, everybody. Pleasure to be here.
And joining us as well is Paul Mansfield. Paul is Principal Hydrogeologist with VI Groundwater Solutions. Paul, we're really glad to have you on our panel today. Thank you so much.
Thanks, Jill. Hi, everyone.
All right. So with that, I will now just run through for you, the participants, how you can interact with our panel today, how you can ask questions. Firstly, this is a webinar, so you are muted and your video is off by default, so you don't need to worry about finding those settings. To ask a question, you can enter it at any time during this webinar. We will run for 1 hour until 9 a.m. Arizona time. There is a button on your Zoom control panel that says Q&A. And you can click on that and you can enter your questions into that. It will open a window and you'll be able to type in there. You'll be able to see others' questions as well. You can upvote questions using a little thumbs up. So if we have some questions that are higher rated, we will pull those to the top of the queue. You can click a button that will allow you to enter questions anonymously. That is an option. And just to let you know as well, this is a recorded webinar. We will be posting it both to the Watercourse site and also to the GCE's YouTube page, where you can go and find a number of previous webinars on varying geotechnical topics in mining, and you can go check those out. And just a quick disclaimer that the views and opinions expressed today are the panelists' own and do not necessarily reflect the GCE or our affiliated organizations. And of course, the content is intended for educational purposes. And if you do need site-specific professional advice, we do suggest that you seek that as well. All right, thank you everyone for joining us. And that is the end of the introductions. So now we will start the Q&A section of this webinar, and I will invite our participants at this time to go ahead and enter questions into the Q&A on the topic of water management strategies in mining. But just to get us going, we'll start off with a kickoff question that I will first direct to Mr. Jeff Beal, and then we can pass around to the panel for additional comment on this topic. So, Jeff, I'll read it out for you. What are some common themes for water management challenges that you currently observe in mining? So I will invite you to start with this to kick off our webinar today.
Okay, thanks, Jill. So that's a good question. So I think to say that a couple of things that are high on my radar with various projects at the moment are firstly water supply. I'm seeing more and more operations which are not struggling with water, but trying to optimize their water supply and their site water balance. I was at a operation last week in northern Canada where they had some issues with they had a reasonable amount of water on site, but they had some just engineering issues extracting that water. So that's sometimes an issue. And other mines just their the resources, and particularly with the environmental constraints that are put on mines, the ability to get enough water is becoming more and more of a challenge. So water supply is definitely high on the list. And the other, I guess, is the slope stability and the role of water in slope stability. I think we have a lot of challenge at the moment with particularly older mines that are mining slopes at a somewhat lower a factor of safety. They design slopes to factor of safety 1.3 or 1.4, but find they can't make the economics work at those factors of safety, so they've got to switch more to a observational mining approach with lower factors of safety, and that requires very, very good depressurization usually to make sure that they don't start to create instability because of water. I mean, what the water's in any geotechnical environment or slope management situation, the one thing you can control is water. And so it's really important to put the resources into getting the water and the water pressure as low as you can. Always the if you look at the options of how to manage an unstable slope, one is depressurize, two is to unload the top of the slope, three is to buttress the slope, four is to flatten the slope. All of those are very expensive except for the water. The water is always the least expensive option. So we're seeing more and more of that mines are looking to get very, very low pore pressures in order to optimize their slopes and enable them to mine at a lower factor of safety than they would otherwise want to achieve. So those are really, I guess, the two issues that I'm seeing recur more and more.
Thanks, Jeff. Travis, I see you have raised your hand.
Yeah, Jill, I'll add another two to the list. So one is the transition from open pit mining to underground mining. With depleting ore grades and a lot of the large open pits reaching the end of their life. That's another big theme. It does make water management slightly trickier because you've got this massive bowl above your underground workings that you need to manage, big dam, so to speak. And then the other one is sort of assessing, managing, and being adaptive to the risks associated with climate change, and on both ends of the spectrum. Too little water, like Jeff alluded to in his first point, and then too much water as well, with the kind of the more extreme flood events or more frequent storm events. It is something that we need to address as well.
Yeah, and I'll add a further one to that, and Jeff could talk about this one too. But in recent years, we've seen a lot more recognition and study of the role of surface water in pit slope stability. Traditionally, there's been a lot of focus on groundwater and how the groundwater system interacts with the pit slopes and contributes pore pressures that can either affect the design angles or create instability. But there's been a lot of a lot of projects implemented in the industry where a lot of effort's been put into dewatering the groundwater system and controlling groundwater, and yet the slope failures still occur, and somehow water is still a contributing factor in the mechanism. And it's become recognized really that surface water runoff feeding in from the drainages and the crest areas and the facilities around the pits, and that water feeding into the shallow parts of the pit slope, into shallow dipping structures and into weaker rock mass in the excavation damage zone, is often the main contributing factor to slope instability in terms of the water contribution. So there's been a lot more effort made in recent years to really study shallow recharge and surface water and the impacts of those water components on slope stability and slope performance, in addition to the kind of traditional view of groundwater and its impact on the slopes.
Yeah, I just had one more thing. When you get the water out from pumping wells or drains or whatever, that you either use it for dust suppression or whatever in the pit, or you remove it entirely from the pit and you don't leave it to re-infiltrate in unlined ponds or discharging to the benches, because that's just going to re-infiltrate and maybe cause you increases in pore pressures as you move forward. So when you get the water out, you need to remove it from the pit or use it. And obviously, the installations around the pit can often be contributing artificial recharge sources to the pit, increasing pore pressures. So it's often important that you try and deal with that and make sure you don't have ponds leaking in and around the pit sources.
I would also add to the list permitting. Water issues in permitting are becoming more complex and longer with time. And the effect of open pit and discharge is also an issue that is increasing in complexity.
I think that's a pretty good list.
think it highlights the need for hydrogeological expertise in mining and the importance of water. There are a lot of challenges associated with it. We do have a couple questions that are coming into the chat. I appreciate everyone participating today. We'll definitely be pulling those up. Any other additional comments on this kickoff question before we move towards additional questions?
I think we've provided a pretty comprehensive list there. There's some varying topics for sure. So yeah, let's probably move on.
All right.
Can you all hear Jeff, by the way?
You got a bit quiet, Jeff.
Oh, have I? Is that any better?
Your volume decreased.
You're pretty
Okay,
faint.
I'll try to fix that.
All right. Well, I'm going to pull up one of our live questions. All right, so this question was submitted by James. Thank you for the question, James. So I will point this towards our panel and I'll read it out first to give you some time to consider, and then we can discuss. So James's question is stating first that the challenge is quantifying dewatering requirements when provided mine water makeup needs that are more than the necessary drawdown. So how do you determine a dewatering schedule that meets both drawdown and makeup water objectives, especially when permitting may delay these? So great question, James. I do know that in our water course, Simon Scholl did a couple of topics on water balance. Simon, do you think you might want to start with this? We can then pass off to the rest of the panel.
Yeah, sure. I think from bitter experience, you can't necessarily align the two. And whilst the dewatering from pits or underground may be a very valuable makeup source, you can't necessarily align the two because you can't really control where either your makeup needs or your mine dewatering will be going. So I think really what you need to be doing is understanding the limitations of both, to enable you to make informed decisions about where you might need those additional makeup requirements, be that you've got an excess of water in a rainy season and a deficit in dry season, so some sort of medium-term storage solution somewhere on site, or be it a life of mine concept where you may have many different phases of mining and therefore need different dewatering requirements throughout that period, some periods of high dewatering activity and some periods of low. And then, of course, there's the unknown, gold price rockets. You add another mill to your process plant, all of a sudden you need a lot more makeup requirement. So all of these things can have an effect. So I think just really understanding your system, both the limitations and the opportunities within that system, is the best way forward.
Yeah, I think if you have a dewatering requirement that exceeds the makeup requirements for the site, then you obviously need to develop a strategy. So let's imagine you need to pump 100 liters a second to dewater the ore that you're trying to recover, but you only need 50 liters a second as a makeup water supply into the plant. Then you've got 50 liters per second that you're trying to get rid of, you need to do something with, and you need a strategy for that water. So you either need somewhere you can store it, which could be another facility on site if it's an older site and a legacy site that may have some older mine workings or open pit areas or a tailings facility with some freeboard. You could try and find some areas in the mine where you can store some water and pump it around basically inside the mine without discharging it. If that's not an option, then you have to think about a discharge permit, and so then you need to think about the quality of the water that's being pumped, and does it meet environmental standards? Do you need to treat it before you discharge it? And do you need a permit? And it looks like in this case, the person asking the question is concerned about needing a permit and being bottlenecked by that. The other thing that you can do, which was something I did early in my career, was that the dewatering system was bottlenecked by the site water balance. So we needed to pump 100 litres a second to dewater the mine. And the mine manager said, well, bad luck, you can only pump 50, and that's that. So that's what we had that's what we were given as a flow rate for the dewatering project, and it wasn't negotiable. And so what we did is we tried to be very strategic and targeted with the dewatering wells in the pit. So in trying to, dewater the pit on a wide scale basis for long-term purposes, we concentrated the pumping wells into the areas of the short-term mine plan, and just create local drawdown that would enable short-term mining, and kind of move the wells around and have a pumping strategy that still worked with a less than ideal pumping rate. So there's a few things you can think about there.
Thanks, Jeremy. Travis, did you have something
Yep.
to add?
Yeah, just to add, I mean, this is actually a really good question, and there's quite a bit of nuance to the answer. But maybe just to add a bit more. I can't think of a single mining operation that has, where the dewatering requirements match the water demand. So mines typically have, one of two problems: too much water of the wrong quality, or too little water of the right quality, and it's a balance between those two elements. So how you get around that, to maybe touch on the second part of the question, your dewatering schedule, you should kind of treat standalone. So that needs to be driven by the geotechnical and the mining or business requirements. And then you should find as many routes or options to augment your supply. So your makeup water can, anything from stormwater or surface water harvesting, capturing all your surface runoff, capturing glacial melt, snow melt, and the likes. Getting water from a well field offsite, getting water from a municipal or regional water scheme, and build in redundancy in that system, all systems. So make sure you got sufficient storage, like Simon said. Make sure that your pipeline and your reticulation and all your infrastructure has got enough redundancy that if you do fall behind, or you do need to bring in more water, whatever the case is, that you're able to do that. That's from pumps to pipes to dams. And then make sure that your permitting is done in advance, and there's enough flexibility in that permit. So never apply for exactly what you need. Always work in a bit of contingency or a bit of fat in that permit. To give an example, in an underground environment, when you're designing a pumping system, you typically design it for 200% of the nominal pumping rate, and that's to account, that's to bring in that flexibility and redundancy, so that when you have breakdowns, which will happen, that you can then recover, and the same, bringing water in.
Is my sound okay now? Is it better?
Much
Yeah.
better.
Oh yeah, okay. So I mean, I was just going to add that a few mines that I'm working on have started to do aquifer storage schemes. So if you do have excess water and it's good enough quality, you can store it locally in aquifers. There's a couple of mines I'm working at in desert environments where we're doing that, and there's a well field and wells which both act as injection wells and pumping wells. So that's an option in certain environments. Typically, you need decent quality water for that, but it is an option that is on the table in drier climates typically.
All right. Any additional comments or points from other panelists before we move to the next question? All right, thank you so much, James, for the question. I see we do have some more that are entering the Q&A. We have about 30 minutes left in the webinar, so if you do have questions for our panel today, I definitely invite you to put them into the Q&A so we can try to get to all of your questions. I'm going to pull up another. And this one came in from Dauda. So if any of our panelists, I do believe they have experience working in laterites and saprolites. So Dauda is asking, what are the causes of infiltration between the lateritic and saprolite layers, and what are the solutions to prevent instability? So I'm not sure if this could be something you could comment on without the site-specific knowledge, but maybe we can just talk a bit about these rock types and their hydrogeological characteristics and maybe what you've encountered in these types of scenarios. So I will invite anyone on our panel that wants to volunteer to start off with this to either raise your hand or just jump right in.
Yeah, I think this is a very common situation, particularly in tropical regions. And so, saprolites are typically unstable with water pressure, and getting the pressure out is paramount for optimizing slope angles. Whereas laterites tend to be hard, and they tend to overlay the saprolites, and typically in many situations you'll get good surface water runoff from a saprolite, from a laterite, and you'll actually get more infiltration, much more infiltration to a saprolite than the laterite. So the laterite is actually can have to be quite favorable for preventing or minimizing infiltration. But a saprolite, you typically can't pump from it, and so the way that virtually everybody tries to depressurize it is to look at the transition zone underneath, which is often permeable. The people call it the saprock, the transition zone, the oxide zone underneath the saprolite, and that's obvious. That's often heavily fractured. And so many dewatering systems out there have always relatively low yield wells into the fractured material below the saprolite. And the saprolite it's a weathering product, and it tends to be relatively low density, and it tends to have a permeability typically of about 10 to the -5. And so it retains relic structure, so it usually drains down. So if you can depressurize or dewater the permeable material or the fractures beneath the saprolite, then in most situations the saprolite will depressurize enough to give you, 4, 5, 6, 7 degrees on your slope angle. So I think, and often in cases where you have variable laterite, the saprolite performs better when it's overlain by laterite, because the laterite creates runoff and reduces the recharge for the saprolite and makes the depressurization more efficient. So I think the main answer to the question is, when you have saprolite, try to look at the layer, the fractured rock underneath the saprolite, dewater that, and allow the saprolite to drain down. Very few situations can you actually pump enough water from the saprolite, because it has a low permeability. So it has a high enough permeability to drain down, but not enough permeability to allow pumping from the unit.
Very
Yeah,
good.
I've seen some sites that look at some surface water management measures as well to try and minimize infiltration and recharge near the crest areas. So things like lined perimeter drains for surface water runoff, and structures to try and route surface water across the saprolite benches and down onto more competent bedrock benches. It's just part of trying to keep that surface water off of the saprolite sectors as well.
I think good characterization and monitoring is also important, because in lots of places beneath that saprock layer that you're dewatering, pumping from, often you then go back into a very low permeability unit. So if you're monitoring that, you may feel that you're not depressurizing very much or dewatering very much, whereas actually in the saprock layer above it, you're having quite a significant impact. So you need to be sure that you've really understand your environment and you're monitoring those changes and understand what those changes mean in relation to the different layers within your system.
Yeah, if anybody's got a copy of the Derek Martin and Pete Stacey's Weak Rocks book, there's a good section on saprolites and depressurizing saprolites in that book. So the book's called Guidelines for Slope Design in Weak Rocks, and there is a good section on saprolites in that, both geotech and hydro.
And I see Julia has already put that into the chat. Thanks, Julia. A link to that book. Any final comments for Dauda on this question? All right, I think the panel did a great job of answering that. We will move along to the next question. So Mustafa, put this into our live Q&A, asking what is the best system to monitor pore pressure to prevent any kind of instability? So I see Paul, you have raised your hand for this. I will invite you to start off with this question. Thank you.
Okay, thanks, Gillian. Yeah, well, one of the best ways to monitor pore pressure is through the installation of vibrating wire piezometers in and around the pit. One of the great benefits of vibrating wire piezometers is that they enable you to install multiple sensors in the same hole, so you can monitor across faults structures which may be controlling pore pressures within the pit and causing local instabilities due to the hydraulic barrier effect that those structures might be causing. And they also provide you with good data in relatively short spaces of time versus a conventional, for example, open monitoring PVC completed hole, which may take weeks or months in very low permeability environments to stabilize, and it will only give you a phreatic level, whereas vibrating wire sensors will give you pore pressures and will give you differences in hydraulic gradients across structures, which can identify areas of pit instability. So generally, that's the best method. You grout them in, so you grout in with a cement bentonite mix the whole hole, and you'll generally get good pore pressure readings within a few weeks or a month once you've installed them. So you're getting data pretty much in real time after the installation. So that's the ideal system for monitoring pore pressures in most environments.
Thanks, Paul.
Yeah, well, I think it's really useful to have an idea of what types of instability mechanisms may occur in the slope sectors or the pit of interest, and then try and place the monitoring in areas of geotechnical risk or geotechnical concern. So, for example, if there's risk of shallow structural instabilities high in the slope that may have pore pressure as part of the mechanism, then try and gear the monitoring system design and layout towards measuring pore pressures in those shallow structures, and making sure that the sensors are actually placed on some of those structures that may be the potential failure mechanism. Whereas if it's, if the concern is more rock mass shearing and deeper seated rock mass failures are a concern, then placing most of the monitoring into and the vibrating wire sensors into the general rock mass, perhaps closer down to the toe, where rock mass shearing may initiate, would be the best thing to do in that circumstance, right? So the actual monitoring system itself is really important, and Paul's right that the grouted in vibrating wire piezometers that allow discrete location measurement of pore pressure are the state of practice for measuring the pore pressure. But as well as that, actually understanding what you're trying to monitor and where the critical areas are in the pit slope, and actually designing the layout of the monitoring system to address the expected geotechnical risks is also really important.
Yeah, as you say, Jeremy, all this goes hand in hand with geotechnical monitoring. I mean, it's not just the pore pressure component. You have to have instrumented for slope stability, radar monitoring or prisms to identify those areas of instability.
Yeah.
Yeah, and I think, as we've said, that a lot of the geotechnical instability that we have to deal with is fairly shallow to the slope, and so there's a tendency just to put piezometers around the pit crest, but if you do that, they're typically too far away from where you need the information for slope stability. So one of the things we've been trying to do more and more in the last couple of years is put in horizontal piezometers. So you can put the piezometers down on the bench you're mining, and then that'll tell you the pore pressure in the mining bench, and it'll tell you the pore pressure above the mining bench as you mine the slope down. So horizontal piezometers, I think, is gonna become more and more common as we go forward, and you can couple those with a geotechnical TDR system to measure shear displacement as well. So, and they typically don't need to be too deep. Most of the instruments we install horizontally are within 100 meters of the slope. So 100 meter horizontal hole drill from the slope.
And with 6 months to a year of data, you can get a really good idea of what's happening. So some of these, obviously, you're going to sacrifice. If you're putting these in pit, you're probably going to sacrifice them in terms of how long they're going to be monitoring for. But that's more important than just putting them angled in from the outside of the pit, where you might have more years of data, but not as good data.
Yep.
Or not as relevant data.
Yeah.
All right, thank you, panel. Thank you, Mustafa, for the question. Any additional comments here before we move on to another? All right. Considering we were just talking about saprolites, and we may be able to address this one quickly, I'm going to pull up a new question here. Just waiting for it to get in the PowerPoint. I think I was pretty quick on that. So actually, I will go to another one first. Oh, never mind. There it is. Thank you, team. So this question is from Emmanuel in the live Q&A. So talking again about saprolites. So depressurizing saprolite typically is done from pumping from fractured rock underneath, but what can we do when there is no response from the saprolite unit? So Jeff, you talked quite a bit about that previously, very well. Did you want to just touch on this?
Yeah, so I think the first sentence is exactly what we talked about in 2 questions ago. So what can we do when there's no response from the saprolite unit? And another theme is what can we do when we can't get enough water out of the saprock to depressurize the saprolite? So when there's not enough response from the saprolite, typically you're getting depressurization or dewatering in the saprock or the oxide zone underneath, the normal response is to put in vertical drain holes. So they're open through the saprolite into the sap rock or the permeable fracture zone underneath. And so they help increase the vertical drainage of the saprolite. So that's pretty commonly done. The drains will typically need to be very shallow to the slope. And again, that is illustrated in the text that I referenced earlier, the guidelines for open pit design in weak rocks.
The one in the chat.
In the one in the chat, yeah. And then conversely, when the saprolite may be permeable, but for whatever reason the sap rock underneath isn't, then you normally switch to vertical drains, or not vertical drains, horizontal drains in the sap rock or in the oxide zone. And again, there's a good example of that from Cowell in the water book, guidelines for depressurization of pit slopes. In one of the appendixes, there's a case study on the Cowell mine, which had just that problem and had a very large failure because of it when they couldn't pump from the sap rock underneath the saprolite. And they then implemented a very large program of horizontal drains. That was kind of almost 15 years ago, and they're still doing those drains to this day. So that's their primary depressurization method. So, yeah, if the saprolite won't depressurize, but the underlying oxide will, vertical drains close to the slope in the saprolite. If the saprolite will depressurize, but the underlying oxide or sap rock, you can't get the water out of it, then the solution is typically horizontal drains underneath the saprolite.
Good, thanks. Go ahead, Simon.
I was just going to add that in addition to that, again, it's understanding your system. There may be something else that's causing that. It may appear there's no response, and it could be because there's some external recharge source that's entering that saprolite unit. Large waste rock dump on the edge of your pit, perimeter drain that allows infiltration into it. So just being sure you understand your system and pick the correct response accordingly.
Very good point. All right. Thank you, Emmanuel. I'm going to pull up an additional question that we received from our live group. Thank you very much for all of your participation today. You guys have been submitting some great questions. This one is from Henry. And Henry is stating first that a mine has moved from open pit to underground. And then after some time, they had water seeping through the rocks down underground. And because of that, they decided to fill the pit without dewatering. What's your say on this situation? Travis, I'm going to ask you perhaps to first start with this.
Yeah, my say would be it's probably a bit of a problem that they've done that. But maybe just elaborate a bit more on that. Look, I'm assuming there is, some form of crown pillar between the bottom of the open pit and the underground workings, and that they filled the pit with coarse waste rock. So all they've done is they've just buried or hidden the problem, right? They haven't actually got rid of the source of the water. I mean, waste rock, typically has a porosity in the region of 10 to up to 25%, depending on how coarse the waste rock itself is. So they've actually exacerbated the problem potentially. So or definitely. Number one, they're going to reduce any water that they would have been losing to evaporation. So the volume of water that they'll ultimately have to manage is going to increase. The potentiometric surface, so the height, within the pit that's not backfilled, the height to which that water level will reach will increase because you've now consumed a portion of the volume of the pit, of the void space with coarse rock. So structures that would otherwise not have water seeping through will now have water in contact with them and potentially open additional conduits or routes for water to enter the underground workings. It could potentially deteriorate the water quality. So depending on what they're mining, but if there's oxide sulfides, anything that has acid potential, would then further exacerbate some infrastructure challenges underground. Increase corrosion, stuff like that. So probably not the best decision. That being said, if there are certain scenarios where backfilling a pit can be done properly and can actually reduce the risk. All right. So if you geoengineer your backfill where you have some impermeable layer at the base, like fine tailings, for example, with some either penstocks or interception wells or wells that you can use to manage the volume of water stored in that in the backfill, that can actually be beneficial, and that can help you maximize the use of the space, rehabilitate the open pits, reduce the tramming distance or hauling distance for waste from underground to surface. So there are some benefits if you do it properly, but just end tipping or backfilling a pit without a plan is just creating more work for yourself.
You're just burying the problem, I think.
Correct.
Yeah. And I agree. I mean, if you can fill it with tailings. I mean, there's a number of mines put tailings into pits where they're working underneath, and that can reduce the dewatering rate and reduce the recharge, and that's good. But if you do that, you have to be pretty careful that your settlement and subsidence from your underground mine doesn't allow the tailings to pipe and to allow a tailings failure to suddenly go into the underground. So if you put any kind of tailings above the open pit, it's going to build up water, and so you have to really monitor the subsidence and make sure you're not going to create a situation where you get a sudden rush of tailings into the underground.
Yeah, the key is understanding what the relationship is between the open pit and the underground mine before you do any of that anyway.
Yeah, 100%. Yeah. There are a couple of operations, caving operations, that have put cement amended tailings into their pits, and so what they've done is gone with a very high solids tailings, so 63% tailings, and then put in somewhere less than 1% of cement in that, and that actually creates a fairly good, and it increases the strength and reduces the potential for it to migrate into the underground, and it also reduces the amount of water released by the tailings. So there's a couple of operations that have done that quite successfully.
Great. Thank you very much, panel. Any final comments on this question?
Jill, just one last one. The converse of that would be mining open pit above old underground workings. There are many, many, many examples of open pits flooding when they intersect old underground workings. So it's not just open pit to underground, but the other way around as well. Especially in old coal mines, it's a pretty big problem. There's many examples of operations and even fatalities as a result of that. So it goes both ways. But again, to emphasize what Paul said, understand the relationship between open pit and underground.
All right, thank you. All right, next question. I will pull up here. Comes from Amadou. And this is addressed to the panel, so I will actually, I see Christian, you have noted that you might like to start with this question, so I'll call on Christian first to address this question. I'll read it out. So Amadou is asking, what solutions can we apply in the situations where there is surface water seepage along a regional structure which affects the pit wall ramp and slope stability? How do we manage it knowing that for the economic reasons we can't drill a borehole to intercept the water? So how might you suggest that this situation be addressed? Christian, I'll call on you to start. Thank you.
Yeah, I can give a start, and First, I think you need to analyze here the consequence. Losing a ramp is a very serious issue and has a very big economic cost. So by analyzing the consequence, I'm sure that then the economics for solving the problem budgets will be released. Then for intercepting, then surface seepages, obviously try to capture it at source and reduce the infiltration of that surface water seepage as much as possible. That's always the best approach. And then complement by targeting the structure with pumping bores. Using RC drilling and pilot holes, basically to optimize costs. That's also another good way to tackle that. Narrow holes. If you get flow, then you rim it and increase the diameter and put it as a pumping well. If not, then obviously keeps it as just a standpipe monitoring.
All right, Travis, see you have your hand up.
Yeah, Jill, I don't have any technical advice on this one, but 50% of the journey to becoming a good hydrogeologist is being a good lobbyist. So, to get around the economic issues, you really need to work on, lobbying for the work that you want to do and convincing senior management or explaining, the business case, the trade-offs. For those that haven't got there yet, there are some good examples in the course. And the sooner you start lobbying, the sooner you'll get your infrastructure in.
Yeah. I mean, it's very hard to imagine a situation where repairing the ramp and potentially stopping a slope instability that could close the ramp would not have a business case that allowed for some depressurization wells or drains is almost inconceivable. The consequences of closing down a ramp are much higher than the cost of trying to deal with the water problem, almost inevitably.
Makes sense.
It does, yeah.
All right, thank you, Amadou, for the question. Hope that the answers were helpful for you. Any final comments on here? I think we probably have time for one last question. All right. So in this last question, I'm combining one of the live questions that came in and an additional question that we got pre-submitted. So I'll ask Travis. I see you noted that you'd like to start with the top question, but you can also address the bottom question too in your discussion. And then we'll open to the rest of the panel for discussion and final comments. We have about 6 minutes left in our webinar, so I'll read it out and then I'll have you start, Travis. So this question came in anonymously asking, what are your preferred metrics for measuring dewatering system success? And then also our pre-submitted question in the same realm is, what methods can we use to discharge the dewatering water from the project area? So Travis, I will invite you to hit on those questions.
Sure, thanks, Jill, and I'll be brief so we can extract as much knowledge from the rest of the panel. On the first question, preferred metrics, ultimately your water level and your pore pressures are the key KPIs. So those are the key metrics you want to track. There's some supplementary KPIs or metrics that go with that, your actual dewatering rates, depressurization rates, sump levels, dam levels, anything that gets you to your target water level or pore pressure are things you need to track. But ultimately, the key KPI metric is the water level or pore pressure. And then methods we can use to discharge the dewatering water from the project area. Jeff mentioned one. It's something we do quite a bit in Anglo American. It's managed aquifer recharge. So finding it's a pretty responsible technique and method, and it's also really good for water security and water supply. What it entails, for those that don't know, it's essentially identifying aquifers nearby that are not or that don't influence the mining area, and it's re-injecting surplus water from the project or the mining area back underground, either storing it there permanently or banking it for use in future. These systems work really well when you pump water in and pump water out. It works a bit like a bank account, bank the interest and then grab the cream at the end of the month. Another bit of advice on managing discharge is ensure you have sufficient storage, ensure you have sufficient stormwater infrastructure, and make sure you've got the permits for all eventualities that may arise.
Thanks, Travis. Paul, would you like to go ahead?
Just briefly on the preferred metrics for measuring dewatering or depressurization system success. Well, it all goes hand in hand with the slope stability. So hydrogeologists and geotechnical engineers have to talk to each other when you define your targets for depressurization and dewatering systems. They should never be defined just based on the hydrogeology. They need to be defined based on the rock quality and the areas of instability in and around the pit. So it always has to go hand in hand.
Good point, Paul.
Yeah, I mean the metrics for dewatering tend to be easier. I mean in iron ore projects, for instance, a lot of people just track the drawdown and try to get it always 20 meters below the lowest pit floor at any one time. So if there's a rapid advancement of the pit floor, let's say by 6 or 7 benches in 6 months, then you have to get ahead of that. So there's some good examples of that in lots of places. It's typically harder to get metrics for depressurization, but again, identify the piezometers that are close to the potential failure surfaces and use those to track targets.
Thanks, Jeff. We do still have a couple minutes left. Jeremy, Christian, or Simon, would you like to address? Well, I see Jeremy. One or more of these questions?
No, I think just to add to what Jeff said, I mean, if you should, for any major pushback or pit design, there should be some assumed groundwater conditions in the geotechnical design analysis. At the most basic level, that will be a phreatic surface, or it could be a non-hydrostatic pore pressure profile. And in either case, in the slope design, that should be the assumed conditions should contribute to the design factor of safety being met for the slope. And so the piezometric monitoring during pit slope implementation should be used to confirm that the fill conditions are the same as or better than what has been assumed in the slope design. And so if your metrics are geared around achieving pore pressures and groundwater levels that are the same as or better than assumed in the slope design, then usually that's a very good metric for confirming that the factors of safety that have been designed are going to be achieved. Doesn't guarantee that the slope won't fail. It guarantees that the factor of safety that was modeled when the slope design is being achieved.
All
Yeah,
right,
but
Simon, Christian.
a last one, as Travis was indicating, it's always good to raise the water issue with management. So in terms of the watering, success is meeting the mine plan with no delays related to water or having any instability related to pore pressure. So that's really what a management wants to hear about a good, successful dewatering program.
And Simon, anything to add before we close out?
I was just going to quickly add about the discharge, the dewatering system. And again, it's looking at your whole site holistically. If you've got a poor water source somewhere on site, try and use that for your processing so you can discharge your dewatering water if it's better quality. Or conversely, if your dewatering water's not very good, use that for processing and discharge the better quality water from somewhere else on site.
Thanks, Simon. All right. Great questions today. We are just 1 minute over, but I think we hit on a lot of really important topics today. dealing with water in mining. Our panel, you have been amazing. Thank you so much for giving us your time today. We really appreciate it. Thank you to all of our participants for submitting all the wonderful questions. I think this was a great discussion, and I look forward to future webinars with you all. We have a course that I mentioned that if you're interested in hearing more from some of the people on our panel today, our presenters in this course, I welcome you to go check that out. It's all online, so I'll leave this up for a little bit so that you can look into that. And other than that, I hope you have a great day or evening, depending on where you are. And I thank again our wonderful panel. Thank you so much.